Alright, YouTube. Hey, thank you for watching. Um, Oftentimes, I know with myself, I find myself needing a little power supply that I can just dig out real quick when I'm designing something. And what I want to do is make some bias control circuits for this M800 Messenger that I'm working on. And it's just not feasible to deal with big, bulky power supplies and this and that. I found this old HPAC power adapter. It puts out 18 volts at 1.1 amps. I plugged it in, didn't explode, still works. It's a little switcher supply as you would expect. Didn't have a polarized plug to fit the receptacle, so I just pulled the receptacle out and wired the line cord into it. I have to put a piece of ABS or something over that. But anyway, I need a power supply that I can adjust down really low. So, you know, most of the time I just need stuff that I can, you know, maybe run 100, 200 milliamps, or, you know, it could be 2 microamps when I'm putting a circuit together on paper. So having one of these little guys built is kind of a cool thing to have, where I can just plug it in and grab and go with it. An LM317 MBT here, 500 milliamps current limited Motorola. So we're going to put this little guy together here, and that way I can work on this circuit for this M800. And I think I'm just going to mount this guy backwards, like so, and put my parts on this side, put my voltage control pod on this side. So since this guy is already filtered, we don't need any big huge capacitances on it. I think 220 mics on the output of that regulator is going to be super good. And I dug out a 47 at 50 here to put on the input to it. But you know, honestly, I don't even think we need anything on it. Dug out two 4000 series diodes, a 2.2 tantalum 5K pot, 6.8K to put across the 5K pot to make it into a, I don't know what I did with my notebook here. I think the value that I needed was 2.8K. That would adjust this regulator up to about 16 volts, which is pretty high to the ceiling here on this 18 volter. And of course I'm just going to pull the adjust pin the whole way to ground on it. That way I can take this voltage regulator down as low as it'll go. And a 240 8th or 6th watt. I think it's a 6th watt. I like to use these little 6 watt resistors on the adjust pin because they're so small that you can fit them right in between the out and the adjust on the regulators. So that's what I'm going to get started on here today. So first I'm just going to pull these wires through the board and bust a ground path across there with some solder wick. And something I ran into recently here on an entirely different note is this old cheap phenolic board here that I bought a couple years ago, found laying in the junk drawer. Cheap as can be. Here's a piece of vector board. Not cheap at all. Actually pretty darn expensive. But you know what? This board here, you can hit these pads with heat and those pads will not fall off of there. As long as you keep your wits to you. I mean, I wouldn't get too crazy with it and try. But I've never seen a path come off of these guys. Now this, on the other hand, as soon as you hit these guys with heat, those pads are going to fall right off that board. And that's a piece of vector board. So like I said, I'm doing this a little unconventional with the circuit board facing the opposite direction, but I just stuck in my 240 ohm resistor right there and just bust the adjust and the out paths straight down here. So it doesn't have to be exceptionally pretty. So let me see if I can do this with a camera in front of me. This is all I'm doing. So we're going to hang 220 on the output and 47 on the front end of it. And then we're going to throw in some discharge diodes across there, and then we're going to throw in another discharge diode down here. The purpose of the discharge diodes is tantalums can hold a lot of energy, just as well as an electrolytic that's much, much bigger than the value of the tantalum. So if the power supply ever shorts here and this develops a low impedance on this line, and since tantalums are generally considered a low ESR cap, they have a very low internal resistance, which means they can provide a big bang of current. I might have said this in my other videos, just a 10 mic cap can give you like capable of an 80 amp current spike for an instantaneous peak. So if that line were to short, some regulators have built-in resistors to help with this, but sometimes I do this on regulators, sometimes I don't, but I'm going to do it on this one, is to give this cap a discharge path back to the power supply, so when this shorts, the cap doesn't short through the output of the regulator back and damage the regulator. That's why they put these diodes on there. Sometimes you see it, sometimes you don't. All depends. So that cap can just blow right back through these diodes back to the shorted line. So that's that. Got that all tied together. Now I just have to find some minimal load resistor for it to stick on it. So let's just say 15. Let's give it 25 milliamps. So we'll stick a 600 ohm load resistor on it somewhere in that area. Doesn't matter at all, it's just the output of it. Should be under some type of load. Consult the junk drawer here. This will definitely work. 560 metal oxide, but it's got crimped leads on it. Shoot. There we are. Now we just have to put some kind of output terminals on this blasted device. Not sure what I'm going to stick on it yet. Alright, now I just have to find some kind of terminals for on this thing. Man, I hate to use these good Pomonas, because they're kind of few and far between, and they're a little overkill for this project, but so there we go. Cheap little adjustable 2 hour and 45 minutes or something power supply that I can just throw on the table here and trim in circuits that I designed for various applications. I think we can get a half amp out of this for a pretty long period of time, as long as we're not pulling a real low voltage with it, because as you start to get more voltage drop across the LM317, meaning that you have the voltage, the output voltage turned down real low, if you're drawing a large amount of current at a low voltage, you're going to get a huge amount of power dissipation within the device there. So as long as we don't sit there and try to draw 3 volts out of it at 500 milliamps for a couple hours, I think everything will be beautiful with it. You might not think of that, but you know, actually if you run the voltage up to 16 volts coming out of this and you draw 500 milliamps out of it, it's really not a problem, because there's a much smaller voltage drop being across the regulator, so the regulator doesn't get warm at a higher voltage versus running it at a lower voltage. So just a little bit of FYI. Alright, YouTube, got this little power supply plugged in, fired up here, and she's cooking away at 400 milliamps. And these 25 watt Dale NHs are screaming hot. So 9.90, and putting a load on it actually makes it go up by maybe 10 millivolts or so. We jack her up to 16.5. So she's having a little problems holding 400 milliamps under regulation. And honestly, I really didn't expect that. So we're 17 volts, and when we hit 17 volts into 40 ohms is 425 milliamps. So I'm not sure, that may be the voltage regulator limiting, because this power supply should do 1.1. So I think that's the problem we're running into, is the 500 milliamp regulator is just starting to go into current limit at that point. And that's something I've kind of ran into with these voltage regulators. You got to be very careful, because sometimes I think that the specs on these are slightly misrepresented as to what current levels some of these 3-terminal voltage regulators do. Because this one obviously will not hold at 425 milliamps. But that's okay, it doesn't matter for my use. So we'll jack her down to about, see if it holds it. Yeah, it holds at 16 volts, but it won't hold it anymore. So we'll just kind of prove that theory there and see what's actually dropping off as I lay my hand on top of that burning hot resistor. So 18.56 volts is what's actually going into the regulator, and you can see with the load taken off, it barely budges. So right there's a 500 milliamp voltage regulator that's actually going into current limit partially at 425 milliamps. So that's the point that I often run into. Now these things here, these Dale 25s, that's actually 16.6 divided by 40 ohms is 415 milliamps. So 16.6 times 16.6 times 400. Yeah, okay. Do this again. So 16.6 times 414 milliamps is 6.87 watts. You might think that 6.8 watts is not a lot for these guys to handle as far as heat. But if you thought that, you would be wrong, because I literally can't touch that resistor without getting burnt. So it's kind of interesting to note. I think Dale specifies these 25s as being chassis mount acceptable for 25 watts. I could be wrong about that, but I think they just simply call for chassis mounting in order to dissipate that heat. Anyway, successful project. Now I can move on with my testing on my bias boards and stuff with this little guy. So I know it's just kind of a measly little project, but you know, it's just a really helpful tool that you can just pull out to be able to use to power some stuff that you're designing. So nothing really to it, just kind of a helpful aid. So I appreciate you watching very much. Have yourself a great day.